Okay, we're going to attempt to use the molecular orbital theory to determine how stable a molecule of Ne2 would be, as well as predict its paramagnetic or diamagnetic properties, and really just practice using our electron configurations. In order to do this, we're going to start by looking at our valence electrons. So if we think about neon, a single atom of neon would be represented with 1s2, 2s2, 2p6. For the molecular orbital theory, we're only going to worry about our valence electrons, the ones in the outer energy level, so that's energy level 2. We're going to start by drawing our molecular orbital diagram by thinking about the atomic orbitals that we are combining. So the first type of orbital that we're combining would be our 2s with our other 2s. And when we combine those, the molecular orbitals that we're creating are the sigma from the 2s and the sigma star from the 2s, or sigma 2s star. This would be our bonding orbital, this would be our anti-bonding orbital. We've also got our 2p orbitals. So again, we're going to draw those out like that. And then we're going to think about what they're going to combine to make. Two of our p orbitals are going to overlap head-on. And those are going to create another sigma bond. So that would be in a sigma 2p orbital. The other two are not head-on. So when they combine, they're going to actually create pi bonding. So we'll put those at the same level. And we've got our pi 2p, pi 2p. And then we've got our anti-bonding orbitals, same type. So we've got pi 2p with a star. And finally, our sigma 2p with a star. So these in the center would be our molecular orbitals that we're filling. Keep in mind that these two here, the sigma 2p and the pi 2p, can be reversed in order, and for some courses you would actually have to memorize when to put them in each order, but honestly I'm okay with you leaving it nice and symmetrical like this unless I tell you otherwise, and generally I probably would even tell you the order to use. Now we just need to figure out how many electrons total we need. So we think about our atomic orbitals, the ones that we had already filled in for neon, and of course we have two of those. So we'll fill in all of those electrons over here, and that'll tell us how many electrons to fill in our molecular orbitals. So here we need 1, 2, 3, 4 total electrons, so we fill in from the bottom, 1, 2, 3, 4. Here we need 2, 4, 6, 8, 10, 12 total, so again, bottom. And then we still use Hund's rule from back in Chem 1, where if they're equal energy, we fill them in each with one before the other gets a second one. And finally, number 11 and 12 go on top there. So this would be the complete molecular orbital diagram for a molecule of Ne2. You're also going to oftentimes see this as a shorthand method where we don't draw all of the little lines. Instead, we just list our orbitals. Oops, that was an S there. Based on the amount of energy that they require. Like that. And then we just draw the lines for each directly beside it. So the sigmas each got 1, the pi's each got 2, and then we fill in our electrons based on the fact that energy is increasing in this direction. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so there we go. Total of 16 if we include the S's and the P's in all of the sigma and the pi. Based on either one of these diagrams, we can now calculate the bond order. Bond order is equal to the number of electrons within bonding, so that's 1, 2, 3, 4, 5, 6, 7, 8. minus the number of electrons in antibonding, 1, 2, 3, 4, 5, 6, 7, 8, divided by 2, that's going to be 0. And since it's a bond order of 0, that tells us it's not stable. In order to actually gain stability or lower the energy, you need an overall bond order greater than 0. We also notice that there are no unpaired electrons, so based on this, we would predict dimagnetism. And we could just use this idea again to write our electron configuration. So we would just put them in this same order, putting them in parentheses and then telling how many electrons are in each. And that's what it would look like. Hope that helped.